Hello students, welcome to my channel Arun's Physics Portal. In this lecture, I will discuss about the ionization energy of impurity atoms. This topic is meant for BSc and MSc students of physics and electronics. This topic will also be found useful for NET and JRF aspirants. The complete note of the topic is given here for your convenience. I hope you enjoy going through it. Now let us come to the topic. Before we start, it is necessary to have an idea of ionization energy of impurity atoms. The impurity atoms are of two types. One is your donor atom and the another is known as acceptor atom. The ionization energy of donor atoms in a semiconductor is the energy required to remove an extra electron from the donor atom, essentially promoting it to the conduction band. This energy is very small and varies from 0.01 electron volt to 0.05 electron volt. This low energy allows easy excitation of electrons into the conduction band, thereby increasing its conductivity. Similarly, the ionization energy of an acceptor atom is the energy required to promote an electron from the valence band to the acceptor level, essentially creating a hole. For common type acceptor atoms, the ionization energy varies from 0.01 electron volt to 0.05 electron volt. This allows easy acceptance of electrons, increasing the hole conductivity. Okay? You must have read about wave function psi in quantum mechanics. The wave function psi is a mathematical description of a particle's quantum state. It denotes the probability amplitude of finding a particle in a particular position, momentum, or other quantum state. You can think of the wave function like this. The wave function psi x gives information about the particle's position at x, and psi x square, the square of this term, gives the probability density of finding the particle at x. So the square of the wave function gives you the probability or chance of finding the particle at x. So with this background information, we now proceed to find out the ionization energy of impurity atoms. Okay? We have previously seen that a donor atom in a semiconductor consists of a fixed ion of charge plus E to which an electron is loosely bound. Because of the small binding energy with which this electron is bound to its parent nucleus, its wave function extends over a large region. ये इलेक्ट्रॉन जो है लूजली बाउंड है अपने पेरेंट न्यूक्लियस के साथ, तो थोड़ा भी एनर्जी मिलेगी इसको तो डिटैच हो जाएगा. डिटैच होकर कहाँ चला जाएगा ये कहना मुश्किल है. ठीक है, तो इसको पाने की संभावना बहुत दूर तक है. दिस इज द मीनिंग ऑफ दिस लाइन. Since the interatomic distance in a crystal is extremely small, a large number of atoms are included in the region where the probability of finding this electron is large. Under this circumstance, we can think of this electron as being immersed in a uniform polarizable medium of relative permittivity epsilon r greater than unity. This picture is similar to that of a Bohr atom, with the difference that whereas in Bohr's model the electron moves in free space, here the electron moves in a crystalline material. This picture will be valid so long as epsilon r is of sufficient magnitude so that the Bohr orbits are larger compared to the interatomic distance. मतलब कहने का ये है कि हमारा न्यूक्लियस था, इसके चारों ओर इलेक्ट्रॉन घूम रहे हैं डिफरेंट ऑर्बिट्स में. तो जो इलेक्ट्रॉन यहाँ से डिटैच होगा वो लूजली बाउंड है अपने पेरेंट न्यूक्लियस के साथ. तो यहाँ से डिटैच अगर हो गया वो तो बहुत दूर तक जा सकता है. ठीक है, और चूंकि इंटर एटॉमिक डिस्टेंस किसी क्रिस्टल में बहुत कम होता है और इस इलेक्ट्रॉन के बहुत दूर जाने की संभावना बढ़ गई है क्योंकि ये इसके साथ लूजली बाउंड है. तो हो सकता है कि ये जहाँ चला जाए उसके बीच में कई एटम्स जो हैं सो बीच में इंटरवीनिंग मीडियम में रहें। ठीक है। सो द रेडियस ऑफ द nth ऑर्बिट of hydrogen atom is then given by Rn dash is equal to this much. This is the modified radius of Bohr's orbit. ओरिजिनली रेडियस बोर्स का ऑर्बिट का इस एक्सप्रेशन से देते हैं। इस केस में चूंकि इलेक्ट्रॉन डिटैच हो सकता है और बहुत दूर तक जा सकता है, तो उस मॉडिफाइड रेडियस को हम लिखते हैं इस इक्वेशन से। ठीक है। वेयर mn स्टार हियर इज द इफेक्टिव मास ऑफ द इलेक्ट्रॉन। ठीक है। अब देखिए व्हाट इज इफेक्टिव मास। इलेक्ट्रॉन्स इनसाइड ए सॉलिड मूव इन ए पीरियोडिक पोटेंशियल स्ट्रक्चर। ये आपने पढ़ा होगा सॉलिड स्टेट है केस में, which is minimum between two lattice points and maximum at the lattice point. This makes obstruction to the smooth movement of electrons, making its mobility different. Electron thus appear to have an effective mass different from its actual mass inside a solid. The Bohr's theory for hydrogen atom is obtained by putting Mn star is equal to m, epsilon r equal to 1, and z is equal to 1 in equation 2. From this equation, it follows that the Bohr orbit for the donor center are large by a factor of epsilon r compared to that of the hydrogen atom. For n-type germanium, epsilon r is 16 and m star is equal to m upon 4, so that the radius of the first Bohr orbit of donor center is 64 times the radius of the first Bohr orbit of hydrogen. Thus, the proposed picture of the donor center is physically justified. Also, the equation for energy in the nth orbit of hydrogen atom is modified to this expression, En dash equal to this much. This is numerically equal to the ionization energy of the donor atom. The ionization energy of hydrogen atom is given by this expression, and the value is 13.6 electron volt. From equation 3 and 4, we have En dash upon En, the ratio of ionization energy of donor atom upon hydrogen atom is equal to 1 upon epsilon r square m star upon m. Inserting the values of different quantities appearing in equation 5, we get for n-type germanium, En dash is 0.013 electron volt. For n-type silicon, epsilon r is 12 and mn star is equal to m upon 2.4. Hence, the ionization energy for the donor atom in n-type silicon is En dash is 0.04 electron volt. These values are in good agreement with the experimentally determined values obtained from the measurement of carrier concentration and also from infrared optical absorption. The electron contributed by a donor atom may thus be construed to originate from a donor state which lies in the forbidden gap, a few hundredths of a volt below the bottom of the conduction band. Similarly, a hole contributed by an acceptor atom may be visualized to originate when an electron occupying a state near the top of the valence band is promoted into the acceptor state which lies in the forbidden band, a few hundredths of a volt above the top of the valence band. These are shown in figure 1. We are showing you the position of the energy state of donor atom and the acceptor atom here. So this value is very, very small, as we have shown you by actual calculation. Okay. So this is all about the ionization energy of impurity atoms in a semiconductor. I assume you like this presentation. यदि आपको मेरा यह प्रेजेंटेशन अच्छा लगा हो तो इसे लाइक करें, शेयर करें और मेरे चैनल को सब्सक्राइब करें। Thank you for watching. See you next time with some other topic of interest. Till then, goodbye.